Hello! In this video, we're going to evaluate the following integral. Okay, so the first thing I will do is I will divide both the numerator and denominator by cosine cubed of x. So this is what we are doing. And when we do sine cubed over cosine cubed, that gives us tangent cubed of x. And in the denominator, we're doing cosine x divided by cosine cubed of x, which gives us secant squared of x. And we're doing sine x over cosine cubed of x, which gives us tangent x secant squared of x. So next, I will factor out secant squared x from the denominator. And now I will do a u substitution by setting u equal to the tangent of x. And therefore du is equal to secant squared x. So we know for a fact that we're going to re-express tangent of x as u. We're going to re-express tangent cubed of x as u cubed. So then what about dx? What about secant squared x? Well, here's the thing. For secant squared x, we know that secant squared x can be expressed in terms of tangent of x, right? If you recall, there's this identity which states that secant squared x equals tangent squared x plus 1, and therefore we can replace tangent of x with u. We get u squared plus 1. And therefore, because du equals secant squared x dx, I can say that du is equal to that. So now I know that I'm going to re-express secant squared x as u squared plus 1. So this is all good. But as for dx, if I were to take this and solve for dx, I would see that dx is equal to du all over u squared plus 1. So really, I'm just going to replace dx here with du over u squared plus 1. So now we're going to perform the substitutions. So tangent cubed of x becomes u cubed. Secant squared x becomes u squared plus 1. And 1 minus tangent x becomes 1 minus u. And dx becomes du over u squared plus 1. Now from here, notice that we can do u squared plus 1 times u squared plus 1, and we can re-express that as u squared plus 1 squared. And therefore the integral can be rewritten this way. So now we're at a point where we can evaluate this integral by partial fraction decomposition. And so that's what we are going to do now. We are going to use partial fraction decomposition to help us evaluate this integral. And so we're going to do the partial fraction decomposition over here. So what I'm going to do is I'm going to rewrite the integrand right here. Right? But we're going to perform partial fraction decomposition. And notice, these are the two factors we're focused on. For our first factor, notice that it is a repeating factor. So what that means is that for our first one, the denominator will have u squared plus 1. The second one will have u squared plus 1 squared. Since our original factor is quadratic, the thing in the numerator will have to be linear. So I'll write au plus b. But since it's repeated, we have to keep that linear. So we have cu plus d. So that's it for this one. As for the 1 minus u, since it's linear, the thing in the numerator will be just a constant. So all we have to do now is evaluate a, b, c, d, and e. And so to do that, what we are going to do is we are going to multiply both sides of this equation by what we have in the denominator right here. Now clearly I don't have sufficient room to clearly show the multiplication, so I'm going to do so as best as I can. So that's the left side. We're going to do the same thing to the right side. Again, this is not super clear, so I'm hoping you can see that I'm just multiplying this thing on the left side and I'm doing the same thing to the right side. On the left side, what we have in the denominator completely cancels out with what we have here, and we're just left with u cubed. But as for the right side, we have three fractions to deal with. We have AU plus B for our first fraction, but notice that we have a U squared plus 1 is going to cancel out with one of the U squared plus 1s here. We're going to be left with U squared plus 1 times 1 minus U. For our second fraction, we have CU plus D, but the U squared plus 1 squared cancels out with the U squared plus 1 squared, and we're just left with 1 minus U. And for our final fraction, we have E. The 1 minus U cancels out with the 1 minus U, and we're left with U squared plus 1 squared. So next, I'm going to expand these two things out. Oh, I realized I made a mistake. I said plus E plus. Well, this should be a, no, there should not be a plus sign though. This is multiplication. And so this is what we are left with at this point. So now what I'm going to do is I'm going to completely expand out everything so that there is no more parentheses, which is going to be a lot of work. So what I'm going to do is I'm going to organize it as best as I can. And here's how I am going to organize it. Basically, I'll show you an example for the first distribution. So it's going to basically have a total of 8 terms when we fully expand it out. For our first term, we have AU cubed. For the second term, it's minus AU to the 4th. For the third term, plus AU. For the fourth term, minus AU squared. For B now, we have plus BU squared, but I'm going to align it up with what we have here, right? The U squareds are lined up. Then we have minus BU cubed. So again, I'm lining it up just like that. And I'm going to keep doing that. So then plus B, well, I'm going to need a new slot because that's a constant. Then minus BU, I'm going to line that up with what we have here. And I'm going to keep doing that for the other distributions. So I'm just going to keep going. And so this is everything, completely lined up, right? Now here's the thing. Overall, U cubed is equal to 1U cubed plus 0U to the 4th plus 0U plus 0U squared plus 0. So what that means is that A minus B should equal 1, negative A plus E equals 0, A minus B plus C minus D equals 0, and so on, right? And so we can establish a linear system from this to solve for A, B, C, D, and E. For our first one, it's A minus B equals 1. For our second one, negative A plus E equals 0, and so on. And so really, we have a linear system of 5 equations. And if you were to solve for A, B, C, D, and E, you would get the following. So this is the solution to this linear system, and that's really what we're going to be replacing A, B, C, D, and E with, is these numbers. So now we're going to actually perform the substitution into here. So really, this just becomes so this is what we get. And so now, that's really what this integral becomes. The integral of this is the same thing as taking the integral of this thing. And so now, we're going to move back up to the top and write the integral of this thing. So this is our integral now. So really, we have 3 separate integrals we're evaluating, right? The integral of this, this, and this. So, for the first integral, I'm going to factor out a 1/4. For the second integral, I'm going to factor out a negative 1/2. Right, and for the third integral, I can actually evaluate this one right away, right? Or I'm assuming that you guys can evaluate this integral pretty easily. It's going to be minus 1/4 times the natural log of the absolute value of 1 minus u. Right, but really at this point, there's really 2 integrals to evaluate. And so I'm going to call each of these integrals a name so that you know which ones I'm evaluating. I'll call this integral number 1 and integral number 2. So, integral number 1. So to evaluate this integral, what I'm actually going to do is I am going to go back to what we had in terms of x, because originally everything was in terms of x, and it turns out it's going to be really nice if we convert this back in terms of x. So, u is equal to tangent of x, u squared plus 1 is equal to secant squared of x. We know that du is equal to secant squared x dx. It's going to be really nice if we re-express it back in terms of x. Because notice that secant squared cancels out with secant squared, and you're left with the integral of tan x minus 3, which is a pretty easy integral to evaluate. Right? If you recall, the integral of tangent of x is the negative natural log of the absolute value of cosine x. And the integral of 3 is, of course, 3x. And so this is what you get for integral number 1. Right? That is integral number 1. Now we have to evaluate integral number 2. Integral number 2. But again, it's going to be really nice if we rewrite this all back in terms of x. So again, u will be replaced with tangent of x, u squared plus 1 will be replaced with secant squared x, du will be replaced with secant squared x dx. Now, really we have secant squared x squared, which leaves us with secant to the 4th of x. And then du is, again, secant squared x. Now, from here, we can notice that secant squared over secant to the 4th is just secant squared x in the denominator. Now, to evaluate this integral, what I'm going to do is I'm going to break this up into two parts, right? It's going to be this over this minus this over this. So now what I'm going to do, I am going to actually focus only on the integrand, and I'm going to rewrite it in a different way. We're just going to do a little bit of algebra and trig identities. Well, I'm going to rewrite this back in terms of sine and cosine. So really we have sine x over cosine x, but then 1 over secant squared is equal to cosine squared. So I can write it like that. And then 1 over secant squared is just cosine squared. Cosine squared x over cosine x is just cosine x. So we're left with sine x cosine x. Sine x cosine x is 1/2 of the sine of 2x, right? If you recall, that's a trig identity that you guys should know about. But I can also re-express what cosine squared of x like this. If you recall, that's an identity for cosine squared of x. So we've written this in terms of sine of 2x and cosine of 2x. And so then from here, if I distribute the negative 1/2 across and then rearrange it a little bit, you can rewrite this as. And so now I'm going to re-express this integral using this new fact. So the integral of this is really just the integral of this. And so then if you were to evaluate this integral, you would get that the answer is this. So you have integral of 3 separate pieces. For the first piece, if you were to evaluate this integral, you would get this. If you were to evaluate this integral, you would get this. And if you were to evaluate the integral of 1/2, that's of course minus 1/2 x. So this right here is the answer to integral number 2. So now we can re-express this entire thing using this and this. So I'm going to replace integral number 1 with its answer. And I'm going to replace integral number 2 with its answer. And after this, we just have the answer to integral number 3, right, which we have already evaluated. I'm just going to replace the u here with tangent of x. And so at that point, everything will actually be back in terms of x. So now we can put a plus c there. Now I could call this my final answer, but again, if you know me, I like making things look really nice, right? I like when things look nice, so We have to keep going. I like that one. That one's good. We have to keep going. That was good. Okay. So if we keep going with this, so continuing going, we can distribute the 1/4 across, you get. And if you distribute the 1/2 across, you get. And of course, we just have everything at the end here. So again, in my opinion, we have to keep going because I like making things look really nice. We can combine like terms with these two things. And it turns out we can actually make this part look a little nicer as well. And so, by the way, when it comes to combining these two terms, let me just do that off to the side real quick. And we have this thing. Right, so I could factor out a -1/4. And you can see at this point, we're just adding two logarithms. And so if you recall, the rule for adding logarithms is that you can just combine it into a single logarithm. But really, you're multiplying these two things together. Just like that. And if you were to distribute this across, keeping in mind that tangent x equals sine over cosine, you're going to get cosine minus sine. And so this is really what you're left with if you were to actually combine all that together. And so that's why it's really nice if you sort of expand this out a little bit. What this becomes is, right? So notice we have -3/4 x plus 1/4 x. That's -1/2 x. I'm just going to rewrite the sine and cosine parts. Right, so that takes care of this, 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 and this. But as for these two natural logs, it combines into a single logarithm, which is this. So that covers everything, and then we just have plus c. So this is the answer to this integral. So if you were to take the derivative of this thing, then it would result in this, right? That one's a good one, right? I like that. That was good. It would result in the derivative of that thing. And so this is basically the idea of how you could evaluate this integral. And so that's pretty cool, right? And so that's pretty much it.